Okay, welcome back. We want to investigate 6.2 today. And now we're going to actually do proofs of set theory. Um, if somebody asks you to do a proof when working with sets, do not do a Venn diagram, please. As I said before, they will all laugh at you. Okay. Properties of sets. And first off, working definitions for your proofs. And we've kind of seen these already, but what's going to happen is in the proof, you'll want to translate anything like this part given here into a statement like this: x is in A or x is in B. Okay, and that way you can kind of see it as a compound statement. When I use the word statement, I mean the defined proper word that we learned back in chapter 2. Okay, something which is either true or false. Okay, x and these are, I guess, predicates at this point because we don't know what x is. But anyways, number 2, x and A intersect B really means x is in A and x is in B. Thirdly, then, x is in A minus B means x is in A and x is not in B. Fourthly, then, x is in a complement means x is not in A. 5, then, a good definition for ordered pairs that are elements of this Cartesian product A cross B. That's the same as saying x is in A and y is in this other set B. Okay, so we want to be able to prove these set identities. And these are things, if you took the topology class, a traditional kind of topology class, maybe not, some modern topology or something where they're looking at knots and things like that. If you're doing like a traditional topology class, you're going to have to be able to do these set identity proofs. It'll be the first kind of problems you see, and they won't teach you how to do it. Okay, so how do these work? There's going to be like a double supposition. So suppose A and B are particular but arbitrarily chosen sets. And then within those sets, you're going to be picking out a particular element. And the book will call these, I guess, element arguments or something. Okay, so within this supposition, you do another supposition. So suppose x is a payback element in some set, blah, 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 blah. This is where the body of the proof will be. So you'll be using the definitions above that I just introduced, those 1 through 5. So you use definitions, those working definitions. Also you may have to use the logic laws, okay, from way back before, like De Morgan's law, the identity law, all that junk. Okay, so it may require logic laws. And another thing it may require is a case-by-case analysis. Okay, in the proof chapter, they actually look at case-by-case type proofs. It's just a kind of a method of exhaustion. Either this is true or this is true. Let's look at the case where this is true, and then we look at the case where the other guy is true. Okay. Okay. And then after you get through all of that, hopefully you're done and you can make your conclusion. Okay, so let's look at one. We want to prove this kind of De Morgan type thing. So prove for all sets A and B, A intersect B complement is the same thing as A complement union B complement. Okay, so here we go. First, suppose A and B are payback sets. And then we're going to do another supposition. And in this part, to prove that two sets are equal, what do we have to do? Well, first we have to prove that A intersect B complement is a subset of A complement U union with B complement. Okay, so we'll do our supposition here, and what we do is we suppose that we have a randomly selected element from this set, and we're going to show through logic and all of that stuff that that randomly selected element is in this set. Okay, and because it's a random element, we could say that it's true for all elements. Okay. So suppose X is a payback element in that first set, A intersect B complement. By definition of complement, our working definition above, we can say that X is not an element of A intersect B. Okay. We can now kind of rewrite that as a true or a false statement, right? So saying that X is not in A intersect B is kind of like saying that it's basically not true that X is in A and B. Okay, so we could kind of say translating this statement into a more of a logical kind of idea, into more of a statement form, like we would have seen in the beginning chapters, translating the statement. We could say the statement X in A intersect B is false. And then to say X is in A intersect B is the same as saying X is in A and X is in B. Just from our working definition that I started with, right? X is in A and B means X is in A and X is in B. So if you have a statement and it's false, the negation of that statement must be true. Okay. Hence, the negation must be true. And then we could use logic, logic laws to negate it, right? So we note the negation of this X in A and X in B is, from De Morgan's, X is not. So we negate that statement, replace the and with an or, and then negate the other statement. Okay. Right. So if a statement is false, its negation must be true. And that's all we've used. Then we want to translate this statement, right? And we use the definition of the complement. So translating, we have, by definition of complement, A is in A complement, or X is in A complement, or X is in B complement. Okay. Then by definition of union, we can translate that again. and say X is in A complement union B complement. Okay? And I think that's what we were trying to prove, right? Let's scroll back up, see where we were going. What we were trying to prove is this, that X element is in that green box there, A complement union B. Oh yeah, we did. Okay, which is what we were trying to show. Hence, it must be the case that this containment holds. Just for abbreviating instead of having to write out those sets again. Hence, the containment holds. Okay. Okay. Now we want to show the other direction, right? So I want to show that thing that I circled in green here, A complement union B complement is contained in the complement of A intersection B. And it's basically just kind of a reversal of the argument. Okay, so 2, I want to show that A complement union B complement is contained in A intersection B complement. Okay, so I do my supposition. Suppose X is a payback element of A complement union B complement, and then you translate it using our working definitions. Hence, X is in A complement, or X is in B complement. And then again, by definition of complement, and this was by definition of union, this X in A complement or X in B complement, definition of union. Now we use the definition of complement. We can write X is not in A, or X is not in B. Okay, so that statement is true. So its negation must not be true. Okay, so note its logical negation by De Morgan's again its logical negation would be that X is in A and X is in B, which is equivalent to writing from the definition of intersections that X is in A intersect B. Okay? So that's not true. Because that's not true, you can say, well, then it must be the case that X is not in that intersection. Okay? So hence, X is not in A intersection B. And then you can, by definition of complement, you could say X is in A intersection B complement. Okay? I feel like I kind of lost myself in that argument, but that's the flavor. Okay, I think my first argument was more rigorous and would definitely fare better under some sort of objective testing of my proof. But hopefully you get the idea. It's a very subtle thing. I don't think she kind of explains it well enough in the book for me to stomach it. You can make what you want of it on its own. The proofs in the book, or the proofs on WebAssign, are obviously just fill in the blank type things. But anyways, that's kind of the idea. Okay, so once you've shown that X is in A intersect B complement, that's what we wanted to show. Okay, by definition of complement, this is true, which implies the containment in this direction holds. So A complement union with B complement is contained in A intersection B complement. Okay. Okay. 1 second. Okay, so there's one of those. I honestly don't think that's kind of a standard type proof. Usually we take those kind of rules kind of for granted. A more standard type proof would be something like number 8 here. And these are kind of easy once you've done enough of them. They're kind of like riding a bike type deal. At first it's weird, but you'll get used to them. So proof for all sets A and B. A intersect B unioned with A intersect B complement is equal to A. Okay. So again, the previous proof kind of had these logical qualities to it, these logic laws from chapter 2. This proof is a little different. We only have to work with the definitions in order to pull it off. Okay, so anyways, let's do our suppositions. So suppose A and B are particular but arbitrarily chosen sets. And then we want to show the containments hold. So first we'll show A union B, or A intersect B rather, union with A intersect B complement is contained in A. Okay. All right, so we'll suppose then X is a payback element in A intersect B union with A intersect B complement. Okay. In particular, we can rewrite that as using the definition. Okay, so from the definition of union, X is in A intersect B, or X is in A intersect B complement. Okay. And now we want to do a case-by-case thing. There's two cases, right? So the first case, let's say X is in A intersect B, right? So we're just saying let this be one case and we'll let this be the other case, and we'll show that in either case the element is in A, okay, which is what we're trying to show, right? We're trying to show that any element in this thingamajig is in this thingamajig in yellow, the ones I just underlined in yellow. Okay, so case 1, supposing then, or let, if you'd rather, X be in A intersect B. By definition of intersection, X is in A and X is in B. In particular then, if X is in A and X is in B, then you could say that X is in A. And that's kind of like a what did we call that back in the day? It was kind of, seems like it was, what was that law called? I've forgotten already. Looking it up really quick. Seems like it was specialization, but I don't think it was. I think that was the argument form. And of course I can't find the stupid thing. My book is falling apart. Here we are. If you have P and Q, yeah, that was specialization from our arguments. Okay, so if you have X in A and X in B, you can conclude that X is in A. So I would say something like, in particular, X is in A, and that's kind of what we're trying to show, right? Then case 2 is kind of the same argument. So let X, B, and A intersect B, complement. By definition of intersection, X is definitely in A, and also X is not in B, or X is in B complement if you'd rather. In particular, again, via specialization, X is definitely in A. Okay, and then in either case, if X, regardless of X being in this first green one here, if X is in A intersect B, it'll be in A. The only other possibility is that X is in A intersect B complement, but again, in that case, it's an A. So in either case, X is in A, and the inclusion holds. Okay, now we need to work with the other direction, right? So 2, then we want to show that A is contained in A intersect B union with A intersect B complement. Okay, so again, we suppose X is a payback element of A. Okay, and then we could do generalizations, right? So again, we kind of have to work with cases, and sometimes it's too obvious, I guess is the spiel I'm going after. What can you say about my chair? My chair is either in my house or it's not in my house, right? It's kind of like two possibilities, and we're not considering maybe a tornado happens and the chair is halfway in and halfway out. Okay? So what am I saying? I'm saying either X is in B or X is not in B. Okay, you can assume that's true, right? It's either in it or it's not. Okay? There's no halfway in this setting. Maybe you do fuzzy logic. Maybe that would work. Okay, but not here. So then we look at these these cases, right? Okay, so I should call this case one, case A, I guess. Case 1. Let X be in B. Then we could say, in particular, then from our supposition, X is in A and X is in B. Thus, by definition of intersection, X is in A intersect B. Okay, this is case 1. Case 2. In this case, let X be in B complement. So in particular then, X is in A and X is in B complement. And then by the definition of intersection, X is in A intersect B complement. Okay, so there's only two possible cases. Either X is in B or X is not in B. If X is in B, then X is in A and B. The other case, or if X is in B complement, then X is in A intersect B complement. Okay. So I conclude then, hence, X is in A intersect B, or X is in A intersect B complement, and thus by definition of union, what do we have? We have X is in A intersect B, or so union symbol, X is in A union B, or A intersect B complement. Okay, and that's what we wanted to show. So hence the inclusion holds. Okay, so we've shown it worked in both directions. Now we can sort of pop out of our suppositions, our imaginary universe of suppositions, and hence the sets are equal. Okay, so these types of proofs, it's kind of like music, you know. You begin, and then there's some drama, and it sort of goes away from home. If you study music theory, it's kind of like you go from a tonic to a dominant, and then you move around, and then you always want to come back home, right? Is it called a tonic? I don't remember. That has been really long. That's been over 20 years since I studied set theory, or sorry, music theory. I've actually studied music theory. So yeah, it's they have that music flavor to it. You know, there's it starts, you know, at home, and then there's some drama, and then it gets back to home. And if you read that book, Adele, Escher, and Bach, that's kind of what he talks about in there. Anyways, let's look at the empty set proofs. So sometimes you'll presume that a set has something in it, and then it'll lead to a contradiction, and you'll then conclude, well, this set must be then empty. Okay, empty set proofs. Usually what you do is you assume set is not empty. If you're trying to prove it, it is empty, and then you get a contradiction. And then you conclude the set must be empty. Okay. Right, so 29 is kind of a funny one. Prove for all sets A, the Cartesian product of A with the empty set is empty. Okay, so we'll suppose that this Cartesian product has something in it, right? First we have to suppose A is a payback set. And then we'll suppose it's non-empty. So suppose there is an element, so some ordered pair x comma y in this cross product A cross the empty set, and then we go back to our definition of cross products way back in the beginning of the lecture. Okay, number 5 here. If x, y is in A cross B, then x is in A and y is in B. Okay, so let's scroll back down. Okay, so thus, by definition of cross product, x is in A and y is in the empty set. Okay. But this is a contradiction. Why? Well, the empty set doesn't have anything in it. The empty set has no elements. Okay? So our the, the 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 problem with our thinking is assuming that there's something in there. So therefore, there must not be anything in this cross product. Okay. 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 So just in general, when you're working with proofs, and we still have some, do we have any more proofs to go? I think we maybe, no, we do have more proofs with functions and stuff. This stuff to me is what math is. Okay, so if you're going into especially pure math, okay, so this is what pure math is. So if you want to become a math major and you're entering sort of what they call pure math. So there's applied math and then there's pure math. Applied math is more like being an engineer. So you're working with mathematics that is applied to, physics or whatever, engineering. Pure math is different though. So pure math would be like doing proofs all day long. So if you don't like doing proofs, don't go into pure math. Right, because you need they will weed you out of the program if you can't do proofs, and it'll ruin your life. Okay, so just be aware, at least in my outing in pure math, 90% of what I did was proofs. I would almost say 100% of what I did was proofs. So just like the stuff that we're doing now, writing these things up, that's all it is. And it's proofs about math, but it's mainly just proofs. So you're not sitting around doing integrals all day long like you did in Calc 2. Okay, this what we're doing right now is what I consider math. Okay, so just be aware of that. Other than that, have a good day. We'll see you next time.